Aye.
Thank you. Okay, so partial pressures today. Partial pressures, that's our new chemistry thing that we're going to look at. And since we've been talking about gases for several weeks now, and looking at them in different capacities, it only makes sense that we deal with pressures of multiple gases at some point. So that leads us into our topic today up here, which is, of course, as I said, partial pressures. Now, I've already put a little given problem up here that we're going to work out in the beginning of class. So, we have in this situation a total mass of 3.4 kilograms of gas. Now, right away, we should note that this gas is a mixture of multiple gases, and they're listed right here. And you'll see later when you get your assignment, you'll have two scenarios of mixtures of gases, and they'll have varying percent makeups of those gases, and they might be different gases than what we have up here. But of course, commonly, based on our standard conditions here on Earth, it's only a few elements we typically find in the gaseous state at different levels. All right, so we'll have 86% of this 3.4 kilograms will be O2, oxygen. 52.4% will be H2, hydrogen gas. And 33.6% will be N2. N2, of course, being nitrogen. Let's draw a picture, a diagram, before we actually start with our calculations. Okay, all right. All right, so let's say we have a container. And also in our given information, we know that this container, I know it's represented two-dimensionally up here, but stretch your mind, stretch your imagination, and picture a three-dimensional object. It could be a ball, whatever you want. It could be even, it doesn't even have to be circular, spherical in 3 dimensions. It could be a cube or a box of some sort. But its total volume is 3 meters cubed, 3 cubic meters. And we're going to look at this just to make it simpler at first. And you'll see why as we move through this problem at standard temperature, 0 degrees Celsius, which is of course what in Kelvin? 273, right. So we'll have to convert that at some point, as you can imagine, because it's always nice to work in Kelvin when we're dealing with our gases, as we quickly learned in some of our earlier problems. All right, so let's say we have, let's represent oxygen as little circles in here, because oxygen is an O anyway. And these are actually O2 molecules. So these are two little guys stuck together. I know I've only represented them as one circle, or imagine them as whole particles. All right, let's do hydrogen as little boxes then. So we have a slightly smaller, perhaps amount of hydrogen. Number-wise, it might turn out to be more, but we're just looking at percents. All right, nitrogen, let's do little stars. So just to recap once again quickly, we have a 3-dimensional volume. So we have that's a little bit redundant there because volume always indicates 3 dimensions. But it's filled with different percentages of these different gases. So we have the little circles being oxygen, little squares here being hydrogen, and little stars being nitrogen. Now, what do we know about pressure? What do we know about pressure? Okay, so what is it?
Force over a given area.
Right, so it's force applied over some area. Now, when we're talking about gases inside of a container, how is the force being applied here? If we remember our kinetic theory. Where does that force come from? How does a gas exert force on its container? Steve is miming the answer over there. I'm just going to translate that into speech. Essentially, we know that at whatever temperature we have, there has to be some sort of motion of the molecules in there, because we know, we did that calculation that temperature results in energy. And it could, yeah. So because these little particles here have energy, they are zooming around inside this container, and every once in a while, and it actually happens a whole lot if you're actually on the molecular level with an extremely large number of moles of each of these gases. There are times when they slam into the walls of the container and rebound in another direction based upon their angle of collision and a couple different factors that way. It's that force, because they have motion, that they run into the container that leads to pressure. So when you blow up a balloon, and you are putting air in there that has been warmed by your body, thereby it has energy and has motion, the air in there is going to be moving around randomly, and it's going to impact with the sides of the balloon, and that's what causes it to, I guess once you tie it off, to be kind of firm. You can squeeze it and it returns back to its original form because those gases in there are running into the walls of the balloon. They exert an outward force. And it's per that area that we define it as pressure. Very good. All right, so let's pretend now that we want to find the pressure due to each one of these gases. So that's what partial pressure is. Add it all together, we'll have total pressure. But let's say we want to know, what's the contribution to the pressure just from oxygen in this case? Or just from hydrogen? Or just from nitrogen? Being that they are not the total, that they're only part, they are partial of the pressure, partial pressure. All right, so does anybody, I'm always curious, I always want to see what you're thinking, so does anybody want to take a guess or a stab of what might be your first step? Keeping in mind things like the ideal gas law or basic mathematics. Divide. What do you think we should do? Just divide. Just divide anything.
Just divide everything.
Convert.
Convert? Like, what do you mean? Because we can do a conversion first if you really want to.
Well, would we like convert all the givens into the like what we are supposed to use, like kilograms into grams?
Wonderful. I like it. Yep. All right. So let's take our first step to be the conversion of 3.4 kilograms into grams. So how do I do that? What's the conversion factor that I must use?
Times 1,000.
All right, yeah. So for every 1 kilogram, that's the unit that we want to cancel on the bottom, I have 1,000 grams. That's what the prefix kilo means, 1,000. Now by carrying out this multiplication, just my kilograms will cancel, and I'll have 3.4 kilograms become 3,400 grams. And in case you forget math tricks in your brain, if you're multiplying by some power of 10, you count the number of zeros and you'll move your decimal place that many to the right. Likewise, if you were dividing by a power of 10, you would count your zeros and move the decimal place that many to the left. So here we have more grams that are in kilograms, so we get a larger number than what we started with, so that makes sense. All right, so 3,400 grams. What other units do I have there that need to be converted? We kind of said this one as well.
Kelvin.
Celsius, Kelvin.
Celsius to Kelvin. All right. So we have 0 degrees Celsius. And what's my conversion there? Plus 273, excellent. Thus, this becomes a rather easy problem. 0 plus 273 is 273 Kelvin. So that wasn't a hard one either. So we'll keep both of these things in mind as we work through the rest of the problem. Volume. Is volume okay? We can deal with cubic meters. Is that fine? We need to worry about anything else? No. Good there? We're good there? Okay. All right. So let's see. Let's start with oxygen here. Now what we're going to need, if we want to plan this out ahead of time, is we're going to need to know the number of moles in each of these in order to eventually calculate our total pressure and of course what we're really looking for, our partial pressure at the end. Our first step then is going to be, we need to know what mass of this total is contributed by oxygen. So this is where this percent part comes in. So we'll take 86% of our total mass here, which is 3,400 grams. And what will we get there? Somebody want to get out their calculator? It's always good to practice. I say this in all my classes, but it's true. Dan, did you have an answer?
2,924.
2924? That seems quite reasonable. So 2,924 grams of our total mass is contributed by oxygen.
Where'd you get the 273?
That's a conversion from Celsius to Kelvin.
Alright.
This is just a standard. If you wanted to convert from Kelvin to Celsius, you would
Okay.
subtract 273 and you'd get back to
0 degrees Celsius.
That's because negative 273 Celsius is 0 Kelvin.
It's absolute.
Absolute 0.
Alright.
That's exactly right.
Well, now
That's where that comes from. Alright, so we have a mass here. And luckily we have a periodic table which has listed for us molar masses. So we can easily figure out how many moles are in this mass thanks to our friend the periodic table.
Thank you.
So what should I do? What should I do?
Molar mass of hydrogen.
What's that?
Molar mass of hydrogen.
Well, let's do
No, never mind. Oxygen.
oxygen, right. So I don't just have one oxygen here, though I have 2 oxygens. So the molar mass of 1 oxygen is what?
16.
16. So the molar mass of 2 has to be 32, right? So we'll take 2,924 and we'll divide that by 32 grams per mole of oxygen, or O2 in this case, the diatomic oxygen. If we would write this out in a more suggestive form, you would see that, of course, here our grams would cancel, and we'd be left with moles. So does somebody want to put this into their calculator?
91.338.
91.38?
Yes.
.38 moles of O2. Very good, very good. Any questions so far? Yes?
Are we going to be using the hydrogen and nitrogen, like, counts and all?
Yes, we will, yeah. We're just going to repeat this essentially for each case.
Alright,
Yeah. Excellent. All right, I'm going to leave this part up here, but to create space, I'm going to erase all this other stuff and we'll do our calculations for hydrogen and nitrogen. All right, so doing the same thing, we'll take 52.4% multiplied by our total mass, which is 3,400 grams, gives us what? Josiah?
1,781.6.
One 1,781.6 grams. So hydrogen occupies the total mass with a contribution of 1,781.6. What should I do next for hydrogen? I think we might be catching on to the pattern now. Steve's indicating the periodic table, and he's exactly right. We have a mass, we know what element we want, we can easily find the number of moles contributed by that.
2.
So,
Point.
let's, 2? Right.
0, 0, 0.
So if we're looking at
No, 16.
hydrogen, it's not just one hydrogen, it's 2 hydrogens. So the molar mass of one hydrogen is 1, doubling it, it becomes 2. So we'll take the 1,781.6 grams and divide that by 2 grams per mole of H2. Calculation? Dan?
890.8.
890.8 moles, so we'll write that over here too. Excellent, excellent. All right, and lastly, let's do this for nitrogen now. So 33.6% times 3,400 gives us what? Calculate. Dan?
1142.4.
Alright, okay, so 33.6% of this total, 1,142.4 grams. Next step,
28 grams.
28 grams? Then you did that by,
Just thinking.
by thinking, that's a good place to start.
Periodic table.
Periodic table, yes. Alright, so, same procedure. We'll take this mass, that is 33.6% of our total. Divide that by the molar mass of 2 nitrogens, just like we did with hydrogen and oxygen, and we'll get, what did we say, 28? 28 grams per mole. N2. Calculate.
40.8.
40.8,
Yeah.
what you said? So 40.8 moles N2. The next bit of information. Can I erase this? Are we good here?
No, I'm good. Talk to you.
Need it for a second? That's fine. The next bit of information that we'll need is the friendly ideal gas law. Because using that, what will we be able to determine?
Pressure.
We'll be able to determine the total pressure. The total pressure. We're good now? Okay. So we'll begin by noting what the ideal gas law is. And does someone want to help me out?
PV or lowercase a.
PV equals nRT. Excellent. All right, so obviously we're looking for P, our total pressure. We know our volume, that was given to us back here. We know R, that's a constant. We also know T.
Oh
That was given to us here as well. And thanks to our initial calculations, we also know N. And since P here will represent our total pressure, we're going to want to look at our total number of moles. So does somebody want to add up these three numbers for me?
Let's see.
You're not gonna do it. Maybe 1,022.98.
1,022.98, is that what anybody
That
else
would make
thinks?
sense.
1,022.98, you said?
Yes.
Yes.
I'll tell you what, just for ease, let's just round this to 1,023. So now we know N. So we have everything that we're looking for and we know what we want. Total pressure right here. So let's start filling this in. So P times our volume, 3 cubic meters, times our total number of moles, which is 1,023 moles. What is R?
Constant.
0.082.
And what are our units?
Liters times atmosphere.
Yeah.
In this case, it's not liters. Meters cubed. Times atmosphere.
What is it I kick in?
I'm trying to whisper with the video.
That's okay. What are our units? We'll see if we need to fix anything.
Atmosphere times, well, are we using cubic meters in this one and not liters? Because it was liters before.
It was liters before?
Atmosphere times meter over, I think so at least.
All right, well, let's just write it up there right now. So,
Over moles times Kelvin.
like that, right?
Yes.
Okay, and we have our temperature that we calculated to be 273 Kelvin. All right, so our only problem right now is that we have a volume of cubic meters here and an R value that has liters in it.
Yeah.
So does someone want to look around for maybe a conversion between cubic meters and liters? See if there is one, if there's anything we need to do. Go ahead, consult your books really quickly if you have some sort of internet connected device. That would also be an applicable choice here.
Siri.
Not fair.
It's not that useful.
I don't like Siri.
One cubic meter, 1,000 liters.
1 cubic meter is
1,000 liters.
1,000 liters. That we get 1 cubic meter per 1,000 liters.
I had to tell you this.
All right, so let's do that. Let's do that over here. So 1 cubic meter. Actually, I'm gonna write it in a better way. What do we say, 1,000?
Yes.
So 1,000 liters per 1 cubic meter. We can multiply that by 3 meters cubed, so our meters cubed cancel out, we're left in liters. 3 times 1,000 is 3,000 liters. There we go. All right, so now we can go back into our equation here, and we'll try to squeeze it in. $3,000 liters. All right, how should I solve for P now?
Divide those 3,000 liters away.
So divide both sides by 3,000 liters. So we'll get a pressure, a total pressure. I should indicate that. Someone want to do this calculation here? Practice, practice, practice. Get used to your calculator.
Talking about practice.
Not a game, practice.
And I'll double check with mine since this is a little bit of a tougher one.
Not the game.
I think,
You're not committing.
I'm not committing it.
All right.
If it's right, then I know for a fact that the pressure is 7.63 atoms.
Very good. We can go to three decimal places here, or 3 significant digits, so 7.63, yeah, that would be good. 7.63, and our units here would be atmospheres, because that's what's in our constant there.
What's under P?
Total,
Oh.
TOT, I can write it.
LOL.
Total, there we go. All right, we're very close now. We can almost do our whole partial pressure calculation. All that we need to do now, listen up, we're close, we're very close. All that we need to do is find out what percent of our total number of moles is for each one of these. So how should I do that? Divide?
Answer's always divide.
Maybe you should times.
I think I should do this for each one.
Yeah.
Or you should plug it in, you shouldn't.
Keep doing that.
91.38 out of our total.
Yep. Divide in.
90.8 out of our total. And 40.8 out of our total. And then multiply each one by 100. To get our percents. So let's see. 91.38 divided by 10 to the 23. So this is 8.93%. %. 3.99%.
I'm off it right now.
All right. So to get the partial pressure, so we'll say the pressure just due to oxygen is equal to our total pressure, 7.63 times the percent that is due to oxygen, so 8.93%. Partial pressure due to hydrogen is going to be 7.63 times its percent, 87.1. And the partial pressure due to nitrogen, surprise, surprise, it's 7.63 times its percent. I won't worry about carrying out those calculations here. I'll let you do that on your own in your calculators because it's our final answer there.
Is that all?
You trying to be a jokester?
I'm trying to be.
Do we have any questions? Any steps that aren't clear?
Got it.
You times by 100 every time.
Every time?
Yeah, like at that one time.
Yeah, because that's to get the percent.
That's just to get percent.
Yeah,
Yeah.
that's what I thought. That's what I thought. Or you can times it and then times by 100.
All right, I'll tell you what, if there aren't any other questions, we will take our break and then we'll work on our assignment.